Okay, let's get started. So before we start, next week you won't have lectures at all. Great. Yes, only temporarily. As we talked about, so next week I am traveling to Shanghai for a week, so I will be missing. You might say, "Oh, it's good for professor because I'm not going to give you 2 lectures, right? I will have to give 5 lectures instead." So it's actually not. So it's going to be a tough time for me. But anyway, so next week we want to lecture. I will announce on the KLMS website. But we will have to make up at some point, as we talked about. We will pick evening and then crash it. Okay, so that's the plan. Yes. So that's the. Oh, that's the good news for me. No, actually, so I was about anyway. I have a schedule on that day, regardless of the interview for undergrads, because I will be giving a colloquium talk at somewhere else. But I received the email from the department saying that because that's the interview day for all undergrads, either it is recommended or I'm forced to cancel the class. Either of the two. So I will check and confirm. But regardless, meaning whether it is officially canceled, so no makeup is required, good for me or maybe bad for you, and or bad for all of us, or good for all of us. We want to lecture regardless, but the only question therefore is whether we will have makeup for that or not. Any other questions? Okay, so after this lecture, then we have only 4 weeks left to go, right? Am I right? Before we have final examination, yes? Good, so let's go. So we are developing perturbation theory in terms of Feynman diagrams. And today we will do a whole bunch of calculations of Feynman diagrams and then extract physics information out of it. So that's great. So last time I introduced the concept of Feynman diagram, say, oh, wouldn't it be great if we actually have a diagrammatic representation for scattering amplitude rather than just for the S operator, right? So, and then we say that typical structure of a scattering amplitude is like you have a whole bunch of external momenta. And in the initial state, we're going to have another whole bunch of initial momenta, right? So generically, this will be some horrendous function of all these external momenta. So we want to have a diagrammatic representation of that, an easy way of computing associated objects, or whatever that is, it's going to be a function or meaning with diagrams with this labeling of momenta, right? We talked about it. So again, using the Yukawa theory, Yukawa-like theory that we started using it. So there we had one real scalar and the one complex scalar, and then the interaction term was some coupling constant, then psi diagram psi phi. So we're going to continue to use it. So now, in order to understand the Feynman diagram representation of the scattering amplitude slightly more clearly, let's actually look at a particular example first, and then we extract general lessons about it. So, for instance, we can first talk about first process, n goes to n. And suppose this guy has momentum p1, this has momentum p2. And then the final state has momentum p1 prime and then p2. So basically, when I expand this S operator to get whatever diagram that is responsible for this process, we're going to have to somehow construct a diagram that has 2 coming in and in. And this is representing n with a momentum p1. This represents another n with a momentum of p2. Then another 2 arrow comes out. So this represents the final n, and this represents another final state n, p2. Now, you may recall that, so these are produced or created by this operator psi, which has annihilation operator for n and creation of operator for n, sorry, the n particle, right? We talked about that. And then I told you that if the momentum flow is parallel to the charge flow, that corresponds to n. And if you have, for instance, another example where there is charge flow like that, momentum flow is that, that is the situation where you have to take the physics picture of it. So this represents the n bar. Hopefully you remember that. Okay? So in other words, if this carries charge -1 with the momentum, this carries charge +1 with the momentum. This is an interparticle relation. Okay? So then let's see what kind of diagram we can come up with this. So at order G squared, in other words, at second order interpolation theory, that we want to expand this. So then we have the following diagrams. So there's this. Again, move in. So this represents n, another n, and I'm being careful, but I will be a little bit sloppy momentarily. This is n, P1 prime, P2 prime, and then there's going to be some momentum flow through this line too, which represents this phi. So I'm going to call the state that is created by side diagram as n and n bar. Then the state produced by phi is just pi. Historically, there's a nucleon and pi. So we're just using that nomenclature. So there's going to be pi here. And so let me label the momentum that this guy carried to be Q. Okay, so there's that guy. So this diagram, let me call A, diagram A. And then I can draw another diagram. So, and then here, still, I have not completely switched to Feynman diagram picture yet. I'm about to establish this real quick. So therefore, let me just still label the vertex 1 and 2. So here's the second diagram. Okay, so now I'm just going to be already sloppy. So these are all n's and pi. You now understand that. So instead, let me label as this P2, P1, P1 prime, P2 prime, and there's going to be some Q, which we will determine right away. So again, I'm labeling the vertices 1 and 2. I'm still doing it. Good. So there are another version, which is, let me just draw here. So let me just flip around the vertex 1 and 2, which you would consider in Wick's expansion, Wick diagram, right? So you look at all permutations of vertices. So let's do that. If I do A here, I have 2, 1, that gives me, so if I only flip the 1 and 2, P1, P2, P1 prime, P2 prime, and then all arrows the same. So let me pull that to the C. So that's the same thing here. So again, I'm just permuting the diagram first, and then with the labeling. So P2, P1, P1 prime, P2 prime. That's close. So here, in these diagrams, time goes from left to the right to the left. Okay, and this is the Coleman convention. I have never used it before, but I have to now. And Coleman's idea is because, yeah, this is initially final, so let's draw according to that structural equation. So now, so let me call this diagram to be D. So the only thing that I have done is that first I just draw a Wick diagram, and then I just start giving a name, the labeling with the momentum. Now, good. So now let's first determine this Q. Let me write here the Q. So by momentum conservation, 1 comes in, 2 comes out, right? So you determine Q. So it should be P1 minus P1. Again, 1 comes in, 2 comes out. Here, my convention is this. So it's going to be P2 minus P1. Now, if I do the same thing here, because I have not changed any momentum labeling at all, Q is going to be the same as A. So it's going to be P1 minus P1. Here too, the only thing I have done is I exchanged the labeling of the indices or vertices. So Q is going to be the same, P2 minus P1. Good, done. Okay. So here is the statement now. So this is fact. So now I'm gonna make the statement. Since scattering amplitude is a function of the external momentum, right? A and C, which are related by just permutation of the vertices, have the exact same momentum structure, including internal momentum, right? So there's no way these two give rise to different answer because it has the exact same momentum structure. So this will give the same answer as that, meaning it will return some function which is the exact same function of momentum. Similarly, A and so therefore A and C will give the same answer. B and D will give the same answer. Okay. So therefore, what is the lesson here? If you draw a diagram and then you want to assign momentum for external lines, any diagram which is related by the permutation of the indices or vertices, will result in the same answer in the scattering amplitude. So overall structure is this. So if you look at the nth order perturbation theory, so if you imagine of expanding S operator in the context of this again amplitude, not an operator. So S is an exponential. Okay. So nth order you start with the order of n factorial because you're expanding the exponential. Now, so then again, this is extended by the state. Okay. So then this will give rise to some diagram. Let me just pull a diagram with the vertex 1 to n. And then there's gonna be always other permutations of vertices. One left. So overall, this will be n factorial number of them, right? I can always list the dependent for number of them. So you see that therefore, like I told you, they all make the same contribution. So it's as if I just look at a single such diagram without worrying about the permutation of vertices. Is that clear? So therefore, I will represent the entire set of this thing as a single final diagram. And without labeling, now it doesn't matter, the vertices. We'll forget about the vertices completely. Understanding the fact that the single diagram represents the entire sum of diagrams which are related by the permutation of the vertices. Okay? So that is the key idea. So now, therefore, this will be the single final diagram because again, I'm just going to erase 1 and 2, 1 and 2. If you do it, obviously, this is exactly the same as that. I don't have to look at it. Now, A, on the other hand, is going to be different from B. If you compute it, which we will do momentarily, A will give you a different answer because this is different momentum assignment than this. In particular, for instance, Q here is different from this Q. So different momentum assignments of the external legs will contribute to the different answer. So that you have to separate. Okay? So that's the idea. Good. So now we are going to compute this, and then we are going to compute, first of all, honestly, by actually computing this object. Okay? Then we will figure out, by actually computing this object using just algebra, we're going to do it, and then we say, okay, then in order to say that these represents perturbative representation of this thing, what are the rules you have to assign to each of the vertices, internal lines, in such a way that you can say you're actually computing things using diagrams, right? So that's going to be the final rule that we will extract, and then we will explore a couple of physics examples. Okay, that's the goal today. Let's do it. Good. So therefore, we're looking at n and n goes to n and n process at second order invertibility. which I usually just write it as a powerless coupling. So therefore, the key object compute is this, which include at this order, so 1 over 2 factorial, then minus ig squared over 2, because there's minus I, and this thing has G, sine negative sine phi. So if you look at the second order, you're going to get the minus IG squared for sure. This is factorial, if you like, doesn't matter. Good. Then you have integration over 2 vertices. Again, I'm just computing it, okay? And then we're going to make a relationship to those items. Then there's P1 prime, P2 prime. And then time ordering of psi 1 negative psi 1 by 1, psi 2 negative psi 2 by 2, and then P1, P2. So that's the computation we're going to have to do. And we know that a particular diagram that actually contribute to this thing is the one with the contractions on phi's. Okay, so far so good. Sorry. Everything is fine, but out of the time ordering, I'm extracting a particular normal ordering. That's not it. Yeah? Remember, Wick's theorem, it contains that with a coefficient 1. We went through that. Good. So now I can massage this just a little bit. First of all, you know that contracted case is actually not an operator, so I can just take that out of the normal ordering whenever I want to. So let's do it. So by 1 by 2, contracted, and then we want to the time, normal ordering, side 1, side never, side 2. Wait a second. Did I write this right? Yeah. Accidentally, I did it right. Okay. So in order to finish this computation, I just need to know this. I just need to know that. I just need to know how to do this integration, right? So let's do it. First of all, okay, let me call this piece to be just 1. Then I will compute. Then this piece to be 2. Then I will just compute 2 real quick. Well, I just gotta tell the answer. So let's focus on the first piece. Now, what is the physics here? There is a state already produced, which are 2 end states. Then what this operator does is that you take those in state and then get rid of them at the vertex. And then you produce them again. And then you end it on the final state. Right? That's what's happening. So now this is normal ordering. And you know that psi contains annihilation operator of n. So let me write n there. With minus I theta. Psi neighbors can include creation operator for n with plus I theta. Yeah. So here's the initial thing. I know that I need to have 2 annihilation operator for n, which means that I'm gonna make use of annihilation operator inside of this guy to get rid of them at the vertex. And then I'm gonna use 2 creation operators coming from here to produce 2 of them, and then end it on the final thing. Okay, good. So now then I can write this one as follows. Thus, without a normal ordering. But I will say one more time what I mean by that. So you might say, oh, that's ridiculous. No. So here, let me put star plus. So what I meant was that whenever you see this expression, I'm gonna always make use of this alpha from these guys, and I'm just gonna use alpha daggers from that guy, right? So that's what I meant when I'm writing this is equal to that. Probably I have to start there. Okay? So then you see, if you look at this, this is manifestly normal ordered. So I'm not actually making a mistake here, right? But the star is this thing. Is that clear? All right, so we then understand electrically compute this, and then move on. Okay, so I'm gonna keep it just for now. There's a very good chance that I have to draw that again. Good. So for that calculation, let's recall the following fact. So let's just state the fact, and then if I have P, so momentum P is n state. So here I'm imagining that this is n state nucleon rather than the nth nucleon. So then this will include E3P, 2 over 2P, so 2E, I'm sorry. And then I'm just keeping the P's that corresponds to the nucleon operator, and then this. So that's P. Well, what was the P? So the way we define relativistically normalized state in Fock space, this was defined to be the operator of the P acting in a vacuum. So let me just again put primes here because this is separating momenta as this particular P that I have to keep there. Okay. So and again, because so then what you can do here is that okay, let me just do it. Let me actually do it. I'm gonna do it once and for all carefully. Then I'm gonna speed up pretty soon. X. So I'm just gonna take out which are not relevant for the operator calculation with a vacuum. There's an alpha P prime, and then there's alpha delta P vacuum. Okay, so that's that. Then this is, you know, you can write it as commutator, and then flip like that. And then we learned that this is normal order, and then you see normal vacuum expectation value of normal ordering is 0. Right? So that doesn't contribute. And this one is normalized. So my alpha, there was my alpha, there's a Coleman's A, there's a Pascal's A. Again, I mentioned several times. Hopefully now you can go back at first. So this is 2 pi to the Q, 2E, delta. Okay, so nicely is that because these factors that you might scare off exactly as the denominator. Remember, my slash notation has all the 2 pi in the denominator, right? So they all cancel against that. Now you have just regular D3Q momentum integration with the delta function, right? You can just do it, and then you will be left with e to the minus I. So this is the wave function, right? This is the wave function. So start out of the vacuum, we create a state you add in the momentum, I guess, what is the wave function? That the plane wave, right? Good. Why am I saying this? So now I can use this to compute this. So, yeah. So then let's use that to compute that thing. First of all, that's right. Two. You see, so when psi, when you look at the psi on the P, you get e to the minus I e to x, and then permission conjugate of that is exactly that, right? So looking at that, you're gonna get something e to the minus of IPX with some combination. On this side, you're gonna get with the plus sign. Now, if you look at the Coleman, he said this is equal to the one with the vacuum inserted in the middle. Okay. I think there's a way of justifying this this step that goes from here to there. It's known as the vacuum saturation trick. I don't we haven't talked about it. It's not a deep concept, but there's a way of doing it. But I claim that there's a way of getting the answer without doing this step if you're like unhappy with that. Like why vacuum? Why all of a sudden transition to the vacuum, right? So in order to see that, well, let me say it schematically, because if I do it, it's gonna take 10 minutes. I want to save 10 minutes for that. So let me say schematically and go and actually do it. I mean, it's not a difficult thing at all. So basically what you have is this. So you're going to have alpha from here. Let's call the momentum for this first side to be Q1. And then here is alpha Q2 into the e to the I Q1 dot X1. And then I Q2 dot X. So I'm just writing the annihilation operator piece like that, right? I just wrote it as the 1, 2 label. And then this, the same is by definition is alpha dagger P1, alpha dagger P2 acting on the vacuum. And if you're not, comfortable with ordering, remember that they commute, right? All the commutation commute, all the creation operators commute, all the annihilation commute, doesn't matter which order. Now you're gonna slide through this guy all the way to here. Okay? So when you do that, you first encounter one of these the commutation relations when you do it. Okay? And then you're gonna do another side because you slide it in, then you're gonna get another pair of these equations. And then you have to also slide in this guy too, at least one. Okay? So when you do, so you get the following looking expression. Oh, I really have to keep this expression. Okay, the hard time. Life is decision. Which one is harder to write? Definitely this is harder to write. So that means I have to erase this. Oh boy. Okay. So then if you so let's just look at this bit real quick. So then schematically, well, let's see schematically, or I ended up just doing this. Yeah. Into this, so let's pursue it. Is Q2 E1 dagger plus what? E1 dagger Q2 E2 dagger vacuum. So I have done it once. Okay. Then what? Then so then there's this piece. So this is now not an operator, so there's only this piece. So you see there's this Q2 Fi, and then for this one, we're gonna do it again. So Q1 Q2 dagger, and then the other way around. So Q2 dagger, Q1. Okay, so that's that piece taken care. And then there's the second piece. So that looks like what? Q1 times that thing, but I'm gonna do it the same thing with that one. So that will be Q2, Q2 dagger, Q2 dagger, Q2, everybody. Okay, so I haven't finished it because this one I have to still finish it. So therefore, the last time I'm gonna do is I'll do that again. So keeping the first term intact, plus I'm gonna do that again. So Q1, D1 dagger. The only reason I'm doing this is because you haven't seen this algebra thing much, so I'm just doing it. So that takes care of. Let me just write it. Q2, B2 dagger, B2 dagger, B2. Okay. And then everybody active on the back. So just erase this. It's not fit, so it ended up being doing anyway. So you see, now I have not asked you the question where I have another vacuum here, this guy yet, right? I just look at this piece. Now if you ask which one makes non-zero contribution, just stare at it. So that is non-zero because they're the C numbers. But that is zero because it's normal order. I don't need a normal ordering that actually with that vacuum. Because as long as it's normal order in terms of that vacuum, I can do it. Because I know that there's at least one annihilation operator all the time. That's sufficient. That kills it. So let's look at the second bit. So that times that is good. So that makes a contribution. But the rest is on normal order. So this is normal order, this is normal order. The rest will make a zero contribution. All right? So there are two contributions. One is that times that. the other is that times that. So delta function of P1 minus Q2, and then Q1 minus P2, and then another one is P11, 2, 2, right? So there are two delta functions, 1, 2, 1, 2, 1, 1, 2, 2. All right, so then if you contract, if you do the integration over the momenta with that thing, you should get the following answer. Good. So then I can just write it out. I'm just gonna write an answer for this expression. Okay, so let me first write the expression for that one, which I just worked it out. Let's see, so that's going to be e to the minus, because I'm just looking at that side. Okay, so what is it? So let's first look at the 1, 1, 2, 2 piece. So that's going to be x1 dot p1, x2 dot p2. Okay, plus e to the minus I x1 dot p2, x2 dot p1. Got it? P1 with x1, P2 with x2. P1 with x2, P2 with x1. I just wrote it. Got it? And then the other side is the same, because basically, but with the plus sign. So e to the plus I x1 dot p1 prime, I x2 dot p2 prime, plus what? I'll just exchange x1 to the x2. Because second piece is literally this one with the permutation of x1 and x2. Okay? Good. So we're going to be quick after this. This is the first time we're computing this, so I thought I'll just show every single thing. You see, in this calculation that I just demonstrated, you don't need to have like vacuum plug in the intermediate step. Right? Just do it algebra, you get the answer. Okay, now, so therefore, for this piece, one, it's basically 4 pieces. Right? There are 2 terms here, 2 terms here, there are 4 pieces. Okay, so now let's just work it out. This one is like x1, like p1 prime minus p1, and then x2, p2 prime minus p2. Right? So that's okay. Let me write. I x1, p1 prime minus p1, I x2, p2 prime minus p1. And then obviously, if you contract it that way, it is literally exchanging 1 and 2. So there's another piece with x1 exchange x2. Exact same thing with exchanging. So now you can look at that piece, second piece, what p1 prime with p2, p2 prime with the p1. So that's e to the I, f1. Yes. Hold on. Yes. P1 minus P2. 1, and obviously there's another piece which is to exchange. Okay. Now it's time to get out this diagram that I just erased nicely. So now if you look at this, okay, there's a P1, P1 prime, P2, P2 prime. So now if you look at this is literally, the first piece is literally P1 prime minus P2, that is Q, right? Or actually minus that thing. So that I call it A. And then if I exchange 1 and 2, that's literally C. So this is A, this is C, right? And then here, what just happened was that the P1, P2 are exchanged. So I draw another diagram with the P2, P1 here. Rest is the same. So that's exactly B, and this is D, with the permutation of X and X1 and X2. So that will give the same answer, this will give the same answer. So I claimed that thing at the level of diagram before we compute anything. And here, you're just seeing the fact that by actually computing this thing honestly. Okay? There's 1-2 match. Good. So 1 is done, 2 is quick. And so we will basically write down the full answer almost immediately. Questions? Yes.
P2 prime minus P1이라고 저 정리해 있는데.
Yeah, that's a lie.
P2죠.
Just checking. But it's thing. Okay, any other questions? Good. So that's one. So that's done. So now what about the two is here? Contraction. So contraction, let me just write here. Contraction is which is x1 by x2 contraction. We already talked about it. So this is basically defining above here. It's to the minus and q x. Oh, I should be careful. 1 minus 2, 2 minus 1. Usually you don't care about this minus that much. At the end of the day, I don't think it matters. But I believe it is q squared minus mass of that scalar inside one. This was one of the normal problems that you went through, and if you remember, it was this. Good. So now we can combine everything. So this and that will provide us another factor of 2 because they're the same answer. Okay. This will give the same answer. This will give the same answer. So the answer to that question. So let me now continue to write from here. So the order d squared answer is minus ig squared over 2. But again, there's a 2 because of that. Because of that. We have integration over axis. Done. Oh, okay. Nothing's wrong there. But let me just rearrange the order in the writing. So I'm gonna write the q integration first. Q done. Okay, and then there's q squared minus m squared plus -1. Good. But then the d is integration over equal axis. Then I have to combine all the phases. Basically, I have this times that and that times that. Right? It's a product. So what do you get? So here, I'm continuing in the ground. I have e to the I, so I'm just working on the first thing first. x1, p1 pi minus p2, p1, sorry, and then minus q. And then ix2, p2 prime minus p2. Here, you see, comes out with the extra minus sign, it's going to be plus q. And then you will have a term where p1 is not with exact same thing, but p1, p2 are changed. If you look at this, the only difference is p1, p2 are changed. Okay? Hopefully you feel that this is doable, but it's boundary calculation. That's exactly the two things you want to do. Okay, doable because you can do it, but boundary. So therefore, is there an easier way to compute it? If it is easy to do. All right, so we are almost there. So that is minus ig squared to cancel, and then this will give a delta function, and that give another delta function. Right? Good. So therefore, you get the following. So D for Q. Okay, let me actually put this. P squared minus Q. I'm sorry. Just to save some space. Let's see if I can do it. I Q squared minus M squared plus epsilon. So then I have this with delta functions. Let me just write it carefully. 2 pi to the 4th delta P1 P1 Q. There's another one. P2 plus Q. Good. And then another 2 set of delta functions with P1, P2 changed. Okay, so that's the scattering amplitude. Very good, exciting. And then one more such. See, so because here Q are the same. So this says that the Q is equal to P1 minus P2. This infers is that the Q is equal to P2 minus P2 prime, right? So that means that, let me just say that again. There's a Q, it says the first delta function puts that should be equal to that. And then the second delta function says that that should be equal to minus P2 prime plus P2. Which means that delta function infers is overall one of this thing and that thing, or one of that thing and then combined operation. So that equation, this is the same as saying that P1 prime plus P2 prime minus P1 minus P2 equals to 2. So either you say, I'm going to just write this way twice, or you say, pick one of that, and then enforcing this. Nice thing about the second option is that this is nothing but total momentum conservation. Right? Initial momentum P1 plus P2 should be the same as final momentum P1 prime plus P2 prime. So I'm going to just take the second path. So we can write it as 2 pi to the 4th. So I'm going to therefore replace one of the second delta function with a delta function that is first this thing, which is that P1 prime P2 prime minus P1 minus P2. This is total overall momentum conserving delta function in the physical properties. And then I have this minus IG squared, and then there's this good. Then I can make use of 2 pi to the 4th, one of them to get rid of this dash or bar. So I'm just gonna write it as B4Q. No, actually I'm just gonna keep it. That's better. And then it's bothering, but nevertheless I'm just gonna write it as say P1, P2 minus Q. And then you see there was another one with P1 replacing P2, or P2 replacing P1, times this property. All right, so this is the final expression. Okay, so it's been 10 minutes or 15 minutes of calculation, but that was worth it. So now we can go back and ask 2 questions. Questions so far. So let's rearrange everything. Okay, so that is the answer for the scattering envelope with n to n, 2n to the 2n. At this order, the final expression looks like this. Let's actually look at it and understand the physics meaning of it. So we were computing basically using the algebra equation, exactly the scattering amplitude at that order. And the claim was that somehow that should be the same as these 2 diagrams. With Q here, that was P1 minus P1 prime plus P2, P1. So this means that P1 and P2 replaced. So that Q is, we just look at that, P1 prime, P2 minus P1 prime. Prime. Good. So now we can look at it and then do it. So here's the rules. So that thing, so we computed this exactly, and then we want to say that this comes from the computing sum of this diagram. I haven't defined what it means to compute the diagram. The answer was this. So I'm about to establish the rules. Okay? So what is the rules? To do that, let me first define the following object. So as the operator, first of all, so step number 1, the as the operator, this is an operator, can be always written as 1 plus IK. Here, the only point is that 2 facts. One, I just extracted out the 1 because in the physical processes, you can always have a trivial process. Where you prepare the initial state, you just go through without experiencing anything. So that's the one part. I times something. This means that this T captures some non-trivial physical processes, therefore, right? This is a trivial process, this is a non-trivial process. The reason why I picked out the I is because if you look at here expression, for instance, there's overall I here left over. The rest is just real. Okay? So I want to define T in such a way that reality has, okay, meaning this is a pure real quantity. That's what I mean. So then from this expression, I can define the second point. Suppose I have a final state with the sandwich with the S matrix. This will give you, according to this definition, some delta function of a final state with initial state, right? And there's a total momentum conserving delta function because physics always respect this is P A A. This is some of the final momentum if you like. Okay, you can take like positive for the final state, negative for the negative P the initial state if you like. You can pick the convention. But by notation just means that there's a momentum conservation process. And then I, because there's I there, and then A, so probably A of this. So this is there literally nothing but anyway, you see what I mean. So the F of T and I is this delta function times curly A. Okay, the T is still an operator. Okay, but A is now an amplitude, which is a function, not an operator, as a momentum. Okay, it's known as the invariant finite amplitude. Good. So now with that definition, let's now compare that definition. So far, it's just a naming. Everything is just named. And then let's look at this. So explicit computation, at least for the example that we worked out, first of all, yes, it spits out the correct total momentum conserving delta function. That's that. So therefore, by the matching, I can write I times invariant finite amplitude is equal to minus IG square this integration. And then, okay, let me first write the propagator. And then 2 pi 4 1 pi minus q plus E1. Okay, so I just literally wrote it again. Now, look at this, and then look at this, and guess like what would be a rule for the diagrammatic rule to computing that. First of all, there are 2 vertices here and there, and here and there, and then it looks like there are 2 factors of minus IG. Certainly, G is associated with the vertex, because that's controlling the strength of the interaction at that point. So it looks like this vertex minus I times G. Okay? If you trace back where the minus I come from, S matrix was exponential of minus I times Hamiltonian. That's minus I, or it's conjugated if you extend it out. Good. And then for internal propagator, this is a propagator for this pi. Right? So for this propagator with the momentum Q, we have that. So now, in addition to that, then at each vertex, because there's extra factors. What is that? At each vertex, you infer that, point by point, there's a momentum conservation. So strength is minus I times G, but you have to infer that this fidget is happening in such a way the total momentum is conserved. If you look at this, this is nothing but momentum conservation at this diagram A. And then if you look at the second one, that's nothing but momentum conservation inverse at this vertex. Okay? Good. So I can clarify this one more step. Basically, just work with the delta function. What do you get? So then you get minus I times G squared, and you get even simplified by those. T1 prime minus T1 squared minus M squared. right? Plus E 2. So this final version of that will do. Now you can even simplify. What's the now rules that you attach to the diagram is the following. So at each vertex, you just forget about the momentum conservation. We just put the minus I times G. That's how you see. And then externalize, you don't have to do anything. Why you don't have to do anything? Because all those information you remember about the external lines are captured by these delta functions. Right? It just inverted the fact that there is delta moment conservation. We are talking about scalar particles. That's why that's all that there is. But if it's a bigger particle, there's extra data that you have to put. But for now, let's not worry about it. So at this vertex, put each factor to minus I times G, as we did. And then nothing with the external lines and internal lines. According to the momentum conserving momentum assignment, for the internal line, just write down the momentum space propagator. Right? That's the final answer. Is that clear? So if you now you can draw any diagram, whatever. We're going to explore eventually. But suppose you have this, something like that. I told you, don't worry about the external lines. Right? Put the correct powers of the vertices. And then figure out the momentum that's going through that, write down the final propagator. Done. That's your scattering amplitude. Okay? Good. So now we have gone through this horrendous exercise of constructing the S metric, S operator, weak expansion, and eventually the final diagram, and so on and so forth. It was worth it because then you have to just trust me like religion. Okay, don't ask where they come from, draw it, do it. But you don't know where to come from, why you have to do it. But now hopefully you understand, right? Every single step, and why you can do it. So now erase the memory. No, not really, but you know, somewhere in the deep your memory. Now you can do it, right? So now if you're given a theory, which we will do a little bit more exercise, if you're interested in some processes, draw the Feynman diagram associated with that. Then just follow the rules, write down the answer. That's the scattering amplitude answer, right? That's not trivial physics information. Any question? Yes.
In this diagram,
Yeah.
the dashed line means that it's kind of pioneer and it's something unclusive.
Yeah.
Because of this is corresponding to scalar field, so how can I draw the arrow direction of this?
Okay, so still this is that. So if I draw that way, you see the arrow? No. Okay, let me just draw it. If I draw like that, so you can draw two different lines, two different diagonals, like that, right? So and then this one, since it's neutral, meaning it doesn't carry any charge, so there is no chargeable direction. So then this corresponds to pi n goes to pi n physical processes. This one, you're going against the charged globe. So this is going to be what? Pi n bar goes to pi n bar. And eventually, not today's lecture, we're gonna develop, or we're gonna eventually discuss a deep, interrelationship of all these processes we just talked about. They're all related in some sense. Okay, it's called the crossing and then CPT symmetry. But for now, let's not worry about those deep things yet. Let's just start playing with the calculations since we learned how to do it. Yes.
Is there a kind of symmetric method for Feynman diagram, just like Wick diagram?
Oh, symmetry factor that you have to worry about? Okay, so for instance, for the theory that we just talked about, okay, meaning the Yukawa looking theory that we just talked about with different interaction. For weak diagrams, we have to worry about all the symmetry factors. For this particular theory, for instance, compared to the weak diagram expansion, there is no other symmetry factor we have to worry about. Okay, but then if you want to deal with theories that looks like pi to the fourth or pi to the cube, meaning at each single vertex, it comes out identical particles. Then when you try to draw a diagram with two vertices, for instance, that comes in and then the two particle comes out, two particle comes out, then you have to worry about extra symmetry factors. So then for Weeks extension, there's an original symmetry factor that we have to worry about already, which we worried about already. On top of that, there's going to be extra symmetry factors. Final diagram expansion, we just need to worry about this new kind of symmetry factor. For instance, like that, so if you specify vertex 1 and 2, and then you just start with the 4, 5, the 1, 2, 3, 4, 5. Then you have to determine which guy is connected that way, which guy left behind. So there's extra, diagrams that look the same, even if you construct it slightly differently. So there's extra symmetry factor. At some point, either I make a homework problem or just demonstrate one of that. But for now, I didn't want to take into account that factor because this is obscure physics for now. Okay, so the answer is, in a sense, this is the only theory that you have to worry about symmetry factors. Any other question? Okay, so we just learned how to compute it. Now, what should be the next step? You compute it now. Next step, you have to look at it. So look at it. And think, what kind of physics is it describing? Right? If you miss the last bit, there's no point of computing it. Right? The whole point of computing things is to understand the physics behind it. So if you're just satisfied with the computation done, not even asking whether that makes sense or what kind of physics is inside there, you just waste your time. Okay? So here's our answer. Let's look at it. And then let's look at it. So I didn't write the explicit name. That is called the Feynman rules. Right? That's clear? Okay. For each vertex, internal vertex. Sorry, internal lines. And nothing for the external lines. And you need extra rule that I have not got is that you assign the momenta and determine the momentum internal line in such a way that it satisfies momentum conservation. Okay, so then it's called Feynman rules. Okay, good. So now let's actually understand the physics of this definition. Okay. So so therefore so this is minus g squared, and you can cancel out I there. So A, this amplitude is minus g squared times that thing and that thing plus that thing. Okay. So the first physics immediately is that so this thing is symmetric under P1 extending to P2. Right? So functionally, to look at it, if you just symmetrize it or exchange P1 P2, it is invariant. And obviously, this is enforced by the fact that we are dealing with scalars. Therefore, the physics, in this case, scattering amplitude, must respect Bose-Einstein statistics. And it does. Right? So, therefore, it doesn't matter. You might ask, what about that symmetry, which you don't see manifest? Right? What about exchange between P1 prime and P2 prime? How do I see that? Any guess? So P1 plus P2 is equal to P1 prime plus P2 prime. Right? So therefore P1 prime minus P2, which is moved that way, is the same as P1 minus P2 prime. Yes? So I could have written the second term instead in the form that looks like P2 prime minus P1 squared. Since I'm sure it doesn't matter whether I square this, that form or minus that. So now if you look at that way, yes, it's manifestly invariant to P1 prime, P2 prime exchange. So indeed, this satisfies full Bose-Einstein statistics. That's the first physics. Second physics. Obviously now this is proportional to G squared. So let me not even write it on the say. So bigger the G, bigger the probability eventually. So more often this process happens and so on and so forth. It makes sense to call therefore this to be strength of the interaction. or coupling us. And third, so this is the momentum switching. How does it look in position space? How does it look in position space, right? It's curious to see what that happens. And you know what to do. You just go to the position space, right? Okay. So we can do it. So that means we can do the period. Before that, there's a useful frame. So usually you don't do that, or regardless whether you do it or not. Usually you go to what is called center of momentum frame. Go to the center of momentum frame. Remember, this amplitude is manifestly Lorentz invariant. If you look at it, right? This is some p squared, m squared, nothing else. So it's manifestly Lorentz invariant. So you can just evaluate this function in any frame that you want. You will get the same answer. And there's the name. Okay, so some books call the center of mass frame, but that's not quite correct. Okay, so in this case, what I'm imagining, suppose you have a P1 coming in and then P2 coming in, and then they collide at some interacting point. Then P1 prime comes out, P2 prime comes out with some angle data. So that's the computer that I'm thinking. Okay. So remember, the masses of all the external lengths are the same, right? Because I'm looking at n angles and n, right? Therefore, the assignment can be P1 is equal to some energy. So this energy is going to be depending on three momenta. So here I'm just writing the three momenta as some magnitude of the three momenta in direction E hat. So basically, I'm saying this is my E hat direction. So the energy is going to be mass, in this case, nuclear mass plus momentum squared, which I'm not quite writing now. This is the idea basically. So P2, which is basically the same, right? This is so since I'm in the center of momentum frame, momentum of that guy should be the same size but opposite direction of this guy, right? That's how I can be in the center of momentum frame. So that means I am in this direction. But since mass is the same, energy is the same. So P1 prime then. Now I'm shooting out some other direction, which I call E hat prime, but with the same magnitude of momentum. Why is that? Because energy has to be conserved, right? And then total energy is 2E. This total energy must be 2E. But since these are the identical particles, this energy must be the same as that. So that means energy must be the same, which means the size of the momentum should be the same, other than the fact that they can flow out in a different direction. Yes.
So I'm just asking about why the momentum of P1 and P2 is the thing.
Well, with the minus sign here.
Okay.
So that is the definition of a center of momentum frame. So I go to the frame where momentum always add up to zero. That's what I mean by. So that's the definition of center of momentum frame. So for instance, if you were in a situation where this guy was going faster and slower, then you just boost the back a little bit in such a way that again momentum balance is exact. Good. Now again, then the way I just determined here is based on energy momentum conservation, right? So energy must be the same mass, and so but in order to have the same energy, I have to have the same size of the momentum, but they can have a different direction. So this direction I call E hat prime. And P2 prime similar, so E in the opposite direction once again, because total momentum should be zero. They should go opposite direction. Okay, so this is the center of momentum frame. And in this frame, this expression becomes simple, but you want to keep track of actual feature of it. Let's do it. So today I want to look at least one another process that has a distinct feature compared to this one. Let's first look at it. So looking at that, I can just compute it. P1 prime minus P1 squared is, so I just subtract the four momenta, and the energy component just becomes zero. And that means this becomes 0 minus P plus E hat minus E hat, right? square, right? Just literally subtracted it. So this means that 0 squared minus that square is p squared and get prime minus get squared. So p has square, so p squared, and this is unit vector, so 1 squared plus 1 minus 2 times en prime dot en. Then I can define the angle to be theta. That's cosine theta. That means it's defined 2 times p squared on that theta. Yes.
What do you mean by the comma? 0 comma.
E hat comma.
I mean the first row. Yeah. 0 comma plus.
Oh, this is the four vectors. This is the 0 component. This is the 3 vector component. That was one notation here. Okay. Yeah. Remember, what was this? This was nothing but so that I think it's important to mention. So what was this? This was final 3 momenta minus initial 3 momenta. Right? So let me write that again. So that means p vector prime minus p vector. So let's call that to be some delta vector. So then it's the final momenta, 3 momenta, is equal to initial one with some k. Right? So a particle was flying like heavily like that, but there was another guy was bombarded at the end. Okay? And there's a k. So it changed the direction and flying up. Therefore, this delta is nothing but momentum transfer. Right? So therefore, this is going to be called as minus, because there's a rho minus, because of the signature of the metric, minus delta squared. This is the momentum transfer squared. All right? So let's finish the calculation. So then I can do the same thing with what? 1 prime minus 2 or 2 prime minus 1, doesn't matter. So now, if you do that, what's going to happen? So now this minus that. Now you see that minus that, so it becomes plus here, right? So that becomes 0 p e hat plus e hat prime squared. So everything is the same except there's a plus sign. It's going to be minus 2 p squared 1 plus cosine here. And let's give a name to, so this is like delta, some delta squared, but something different. So we call C. Okay? And the relation between this momentum transfer and that momentum transfer is nothing but I exchange the P1 with the P2 or P1 prime with the P2 prime. Right? So this is the momentum transfer in the cross channel, meaning I just exchange the P1, P2. So that's what this means. Okay? So therefore, with that expression, this can be written very in a slightly more simple expression. Let me do it. So with that, this turns into, so A Fi becomes G squared. So this minus square minus will cancel. So this is minus delta squared, there's a minus sign. So overall there's a minus sign. And then it's canceled by that minus sign. Okay? Again, let me say it again, there's a minus sign from this squaring it, but that was minus of delta squared. And there was minus sign, so I can cancel that minus sign with that minus sign. Okay? Provided as a plus. So delta squared plus m squared 1, because I canceled the I. And delta c squared m squared. That's it. Good. Yes.
Later.
Very good. So I put that regularly usually because if this happens to be the same as m squared, this blows up. So let me just have the secure insurance. If that happens, okay, don't give me exploding infinity, but just say there's one in b, okay? I just go back and look at it. But in this calculation, I will never have a chance to hit that thing. This is positive quantity, this is positive quantity. And the second example that I will discuss has a different feature. So this, you will never hit that pole as a physical process. But we will look at another process where there's a chance that you can actually hit the ball. And then these two will describe different kind of things. Okay, so as for your question, we will never hit that thing, so that's why I just erase the initial issuance for now. Good? Okay, so now we are ready to actually look at the changes in the position space. That was the original question. Let's do it. So this is the function of the three momenta, right? This is the function of three momenta. Oh no, this is just a scalar quantity. That's because I squared it. Right? There's a three vector, but I squared it. That is demanded by Lorentz invariance. So anyway, this is the function of three momenta. So I can do the Fourier transform of this to go to the position space. If you forgot how to go to the position space, right? That's how you do it. Let's do it. I mean, it's going to be extremely awkward if I write, V3 delta stuff. So let me just, for the moment, replace with the K, okay? So that the expression looks non-trivial. So I'm doing the now Fourier transform from momentum to the position space. Of that thing. So K squared, M squared. Okay, I'm just gonna wait 2 minutes and you have the answer. Okay, let's do it. Sorry?
E2 minus mx.
It has that piece. Good.
Yeah.
Okay. So this it has that piece. Let's actually work it out. So 2 pi cubed. And then this is 3 volumes. So there's a azimuthal angle. And then there is a radial direction. And that has this piece, A squared M squared. And then there is this what's called polar angle. Do you call it polar angle? How do you call it? Whatever. Theta. You know what I'm talking about. Minus 1 and that thing I can pick as K R cosine of theta. So what matter we do? So there is K direction. There is X direction. Theta. Just writing it down. Okay. Okay, so first of all, this gives me another factor of 2 pi, so I'm going to get 2 pi squared. Done. And then K squared plus M squared. And let's do it. So 4 over IKR. Then this with a plus minus of minus. So that is what? KR minus KR. By the way, K integration starts from the 0 to infinity and 0 to infinity. Almost there.
In the delta,
Yeah.
we have to consider the angle theta.
Yes, but this data is different from this data. Okay, so good. What I'm saying is that let's look at this and just interpret this as some quantity which captures total momentum transfer. And that data is like basically depending on the angle, the actual size of momentum transfer changes. Right? For instance, if you go along the you throw things forward, but if some come out as a backward, obviously you need to have enormous momentum transfer. Basically kick back. But if you go to the completely forward direction, this becomes 1, this becomes 1, this is 0. Meaning you can just fly out without having any momentum transfer. And then you start increasing angle a little bit, you start getting slightly larger than the momentum transfer. So I'm literally interpreting this as actual size of the momentum transfer. So here, I'm just literally viewing this as a single momentum parameter, if you like. For a given angle, this is a momentum parameter. Okay? And then, therefore, I just change notation simply with that understanding and just doing the Fourier transform. Okay? Good. So let's continue. So then this gives me, first of all, well, let me split it one step, but otherwise we're going to lose it. I 2 pi square r. So I'm just pulling it out. 0 to infinity dk k over a square e to the I dr minus e to the minus h. Okay, now for the second term, excuse me. For the sake of the second term, formally what I can do is that I can change the variable to k to minus k. If I do that, this is even in k, this is even in k, nothing changes. So for the second time, if I do that, first of all, exponent becomes plus IKR, but that case looks exactly the same, except now integration limit is from the minus infinity to 0. Okay, with me? So with that understanding, okay, now I can read all of this. So I guess minus I square r minus infinity to infinity dk k to the minus plus I kr over k squared plus m squared. Done so far? Good. Now we're almost ready to extract the answer. So let's look at this. What's happening? So here is the k, but I slide it into the complex plane of k. But the original integration along the real line. So I'm just gonna travel along the real line. So the answer, the question is, do this computation from minus infinity to infinity. But now if you look at this, this is a regular function of k. Polynomial, this is also a regular function of k, minus infinity, positive infinity, infinity. But this one has a call at plus im minus im. So for that matter, you just rewrite this as k minus im, k minus im. So there are two simple poles. Good? Okay, now we can do it. So the only question left over is whether I close that way or that way. You close it in such a way that you can do the computation, right? Meaning it doesn't render ill-defined. So now that is controlled by this exponential, because whenever you close it, you have to ensure that this is convergent contour. So this, okay, powerful, polynomially powerful. This is exponentially powerful. So divergence versus convergence will be controlled by this exponential. Now, since it comes with a plus sign, I hope to have something I times something here, so that overall it becomes minus of something. Okay, something that dies off as if it is exponentially quickly. And that means that I want to take a piece where k has some real value plus I times the remainder value, which means that this is convergent integration on the upper half plane in the complex k plane, right? So therefore, I have to close up over like that. So first of all, integration is happy direction, meaning you're always going backwards in time. When you say it's happy direction, right? This is happy direction. So I don't pick up the extra minus sign. So then if you do that, good. Minus I over 2 pi for r. And then what? We learned that there's 2 pi I times residue. Okay? So residue, I'm just picking up the residue at this point because I'm looking at plus im pole. So I put im for the k into the, if I put if, that gives me mr. And then, so I'm just reading off the residue at that point. So that gives me 2 im. Good. So that means I get 2 pi, 2 pi, there's 2, so 4 pi r into the minus im cancels im, okay? That I is this. Okay, good. So we have an expression. Let's actually look at it and understand the physics a bit. The diagram we've been computing that looks like this. The exchange of some particle with mass m, right? What does that tell me? Well, I didn't know until I just looked at this, but I just computed this in the point space. It looks like that. So let's actually debug this expression real quick in like 3 minutes. That's only the time I'm given. So first of all, you might be familiar with the fact that, let me first erase this. Yeah, no. Yeah, yes. Let's do it. So now let's extract this out of it. And then I will just entertain one other examples we will work on next time. So, so this was the process. And you know that for massless mediator, by which I mean, if you have a massless first mediator, even though you never thought about that way, for instance, these examples, like massless or gravitational interaction. All of that, you get something like Q over R, Coulomb potential, we get M over R. I'm talking about potential. This is gravitational potential. So for massless mediator, you get 1 over R, right? Now this is modulated by this exponential cutoff. This is exponential factors. So let's try to understand it better. So if I take 1 over R e to the minus mr, and suppose I look at the region where mr is much, much smaller than 1, meaning I just take the limit where the range that I'm looking at is much, much smaller than 1 over R, 1 over n. Okay? So let's just play with this formula for a second, okay? So if I look at the region where I'm just looking at the radius or range of the interaction, which is much, much shorter than 1 over n, then this is almost approximated as 1 over R. Right? It's called 0. Okay. So what does that mean? So now this means quantum mechanically, because you learned the quantum mechanics, this means that by Heisenberg's uncertainty principle, small distance means that the energy is much, much bigger than m. Yes? Does that make sense so far? Shorter distance means a larger energy. Which means that if you do this experiment with enormous energy compared to the mass of it, it says, oh, I forget about the mass. It's nothing to me. Okay? And he says, okay, it feels like I just have exchange of mass in this particle. And it feels like I'm only experiencing 1 over R potential. That's what he says. But then, on the other hand, if you go to another region where now R is bigger than 1 over n, which means that you have an energy budget if it's smaller than n, then it gets very hard to create this particle. You don't have energy. Right? You have to pull out enormous budget, enormous depth from the vacuum, which is a lot only by the Heisenberg uncertainty principle. Right? But you have to pay back eventually. So that's hard to do. So that's why you start to experience this enormous Boltzmann suppression looking chart. It's getting harder and harder to produce it. And so this is called the Yukawa potential. Yukawa looking potential. So basically what happens is that, okay, I have this much energy budget. I'm just gonna, ping pong with this guy. But then depending on the energy that I'm carrying, either it's very easy to do so, like that, or it becomes extremely hard to do so, like that. Exponential separation. Okay? And the last thing that I'm going to say is that, which we will do next time, today is over. If you're not trying to cut it, just time flies. There is no moment in time where this guy actually meets with that guy producing something, right? You just exchange stuff. However, next time we're going to study another process like that looks like that, which is now n colliding with n bar, and then n bar coming out. In this particular diagram, then if you just again do the time slicing, at some point this guy emits and actually produces a particle. So then the real difference that we will see next time is that in addition, instead of today we saw a singularity structure that looks like this in the amplitude. Next time we will see that the singularity structure will actually see that looks like this in amplitude. Now you can actually hit this pole. Okay? So this will actually make a big difference. So just as a spoiler, in this case, if you actually Fourier transform, instead of getting this potential looking structure, you will actually get minus IMT. Actual propagation or actual life. This is IHT evolution time. So you just produce particle with mass m, it has a life. Okay, so anyway, that's the next time thing. So today we will end here and we will continue a little bit longer with this discussion, maybe 1 or 2 lectures more before we move on to the next time. Okay, I'll stop here. I'll see you not next week, the week after. Okay.